date is 12th. What I was saying is that you take any p between 1 and infinity. These are something which may not be written in the book, so I am writing it here. 1 over p plus 1 over p prime equal to 1. Then p prime is called the conjugate of p. Okay. So p is given to you. It's called an exponent. So 1 over p prime is 1 minus 1 over 1 by p, same thing, which is nothing but p minus 1 over p. So we invert it, p prime will be equal to p over p minus 1. That's what we have used earlier. Take a positive and b positive, real numbers. Then ab is less than or equal to 1 over p a raised to p plus 1 over p prime b raised to p prime. This is what Young's inequality is, that we have done it. Now you take x in kn or rn, whatever it is, y in kn, and take the coordinates of x to be equal to x1, x2, xn. Please note it's finite dimension. Okay, n is fixed. So now you look at xi, yi, all right. That will be nothing but 1 over p mod xi raised to p plus 1 over p prime mod yi raised to p prime. That is by the Young's inequality. Now you sum it up. When you sum it up, what you have is I equal to 1 to n mod xi yi. Actually, this is less than or equal to, I have not written that, mod xi yi. 1 over p into summation I equal to 1 xi raised to p plus 1 over p over yi raised to p. Take the same element, divide by the norm of xp into norm of yp prime. That is same thing as this 1 over, you have this. So you have this, this, you take this norm of xp into norm of yp prime into the summation. We can take that because this is independent of I. The summation is over I. So this is summation mod of xi yi divided by norm of xp, norm of yp prime. That is what I have. That is less than or equal to, now you split it into two parts. Norm of xi over xp, norm xp, norm of yi p prime into norm of yp prime. Now apply with a as this one, whatever this quantity that you have. You take a equal to, I'll write it here. Right. So you take a equal to mod xi divided by the peak norm of x. This is your a, right? And similarly, this is your b. Okay. Now apply the Young's inequality to this. What you get is 1. So if you apply the previous part, 1 over p mod xi raised to p divided by this plus this one. That's a simple calculation. So this splits into two summation using the Young's inequality. So remove x 1 over p out. What you get is mod xi raised to p over norm of xp, but raised to power p. That is what the Young's inequality says. Similarly, it is 1 over p prime into mod of yi raised to p prime divided by mod of yi raised to p. This one. This is not yi, this is just y. Okay. My mistake. My writing mistake. I will just correct it. Okay. This is not yi. Mr. This one. But this one is just y. Presentation is hugely taken. Okay, so that line has gone here. That's what I'm worried. So this is one. Now remove this 1 over p. Okay, so this is independent of I. So it comes out. So 1 over p is there. Mod xp raised to p 1 over p is there, right? Into summation xi raised to p I equal to 1 to n. Same thing with this yi also. But now notice that what you have to note here is this summation xi raised to p I equal to 1 to n is actually the LP norm of x. So you have here this one, this stuff, okay, and this stuff. They'll cancel. What remains here? 1 over p. So you get 1 over p. Similarly, same argument, you get 1 over p prime. But 1 over p prime is called the p prime is the conjugate of p. Therefore, 1 over p plus 1 over p prime is 1. So now look at the first step and the last step. Okay? So you look at the first step here. This x 1 over norm of xp, norm of yp prime into summation that xy yi. You push this onto the other side. In the last step, you push it here. So what you get is summation I equal to 1 to 1 xi yi, norm of pth norm of x and p prime to norm of y. This is what is called the Hölder's inequality. Okay. Any doubts here?
Sir, basically norm formula is, sir,
Okay. I'm not saying it's a norm. I'm only using the word. We call it as a norm. I'm not a.
okay sir, then fine.
I just call it as a
Okay.
norm, but actually we will show it's a norm. Just hold for a while. I'll put it.
Okay, sir.
Okay. So this is the Hölder's inequality. Now, if you are not happy with this, you can remove this and write here 2 lines with a p, which is nothing but summation mod xi raised to p raised to 1 by p. Okay. So the 2 lines I will write later if you want to show it's a norm. So you can replace it the double line by a single line. That's all. So that's one.
Okay,
So
sir. Okay, sir.
I don't have I'm not in front of you with the blackboard. Otherwise, I would have done it properly. I'm trying to use the notation of what the answers lecture notes is. Now, what you should understand here is that the summation on the left side, this summation, what I am saying, this summation is a finite sum. I equal to 1 to m. That's what I'm saying. Okay. This is important. This is a finite sum. Why it is so important? It is important because if it's a finite sum, there is no question of convergence. Finite sum always exists. You don't have to worry about whether the limit exists. Now what we do is we proceed to the next step here. We show that the norm of xy raised to p is actually a norm on LPRN. So you instead of this proof, I think I have given to you last time. Can you see it?
Yes, sir.
Okay. This is what I was saying, p prime equal to p over p minus 1. Okay. Now, want to show the triangular inequality that gives you the norm. So what you do is you look at x plus y raised to p. Okay. Why are you taking raised to p? Because I don't want to write 1 over p everywhere. So this is same thing as the this norm of x plus y raised to, okay, is actually what we want to show. Okay. Let me see what is done previously. All right. This x plus y raised to p is the norm. Okay. I'm just taking power. He's taking power p so that to avoid too much of writing. What is this by definition? I equal to 1 to 1 xi plus yi raised to p. We will raise it to 1 by p later. Okay. Now split this xi plus yi p as xi plus yi. Last time I told you into xi plus yi raised to p minus 1. Now you write this is okay. This mod of xi plus yi is smaller than or equal to mod xi plus yi. So you put that less than or equal to and put that here. So this mod xi into mod xi plus yi raised to p minus 1 is one term. That distributes. Yi distributes to this. Now apply the Hölder's inequality. Okay. So you have xi here, summation I equal to 1 to n. This is xi plus. So this is norm of the xp, whatever I have, into the summation, whatever that stuff raised to 1 by p. Okay. This is where you use the Hölder's inequality. Do the same thing here. So what you get is norm of xp here, and this part, what we have here, is p minus 1 into p prime into 1 over p prime. And what you have here is p minus 1 into p prime into p prime. 1 over p prime. Okay. So this is a common element. X mod xi plus yi raised to p minus 1 p prime raised to 1 by p prime into summation. This term is common to both. Take that common term. What do you get here? From the first term, you get norm of xp. From the second term, you get norm of yp. Only thing is, almost we are done, right? Except that we need to have some power here. So this one, we want to get rid of it. All right. How do we get rid of that? That was what I was telling you. So you use this inequality here, which I explained to you. So this one will be mod of xp mod of yp into mod of xi plus yi raised to p minus 1 over p. So that substitute this p prime equal to p over p minus 1 in the previous step. Then that p prime disappears. What you get is this norm of xp, not norm, one norm of xp, one norm of yp into x plus y raised to p minus 1 over p. That p minus 1, you have 1 over p prime, no? That 1 over p prime becomes p minus 1 over p. Right? So here you have norm of x plus y raised to p. Here you have norm of x plus y raised to p minus 1. So the power p will cancel. What remains on the left side is just the norm of x plus yp. So this goes off, or you can divide out if you wish. Anyway, cancellation has to be done. Okay. And what you get is the triangular inequality, norm of x plus yp less than or equal to norm of xp plus norm of yp. After proving the triangular inequality, it becomes a norm. But there is a small hitch here. What is the hitch here? The hitch here is that this part, mod of one norm of p plus one norm of p y into x plus y raised to p minus 1 with the whatever the subscript p, you have to divide it. Division is allowed only if it is not 0. So you split the cases into two cases. When x plus y is 0 and x plus y is not 0. When x plus y is not 0, you divide, you get the triangular inequality. If x plus y is 0, then x will be equal to minus y. But then this inequality becomes trivial. That's it. Okay. So the inequality is obvious if x plus y is 0. Otherwise, it is over. So that gives you the what is called. Somebody was asking me that why do you call it as a norm? Now it is a triangular inequality satisfied, and the norm of x is 0 if and only if x is 0. They are in a way simple matter. Okay. What I wish you to understand here, see this left side is actually a finite sum. I equal to 1 to n, xi plus yi, whatever that raised to p is. By chance, if this fellow is true for infinite sum also, you take the finite sum here, you replace it by an infinite sum on the right side, and then you push the matter. I don't know whether you are getting what I'm saying. Anyway, I'll come to that. So that's one thing. And second thing is a simple calculation. Do that. do it yourself. Nothing great about that. Now we come to what is called the sequence spaces. The story, what I was telling you till now, is in Rn or Kn. But now we are pushing over to spaces which doesn't have finite number of coordinates, but infinite number of coordinates. Okay. So let me explain to you here what the story is. Okay. Now we come to what is called a sequence space. Okay. Just 1 minute. Huh? I have to reset the drawing. Okay. Yeah, almost set. Okay. Now we come to what is called a sequence space. So this is written as a script S. This is called a sequence space. Okay. What are the elements of this one? The elements are sequences. So what is a sequence? X is a map from integers to K. What is this K? R or C. Okay. So how do you write this sequence? X1, X2, Xn, etc. Okay. Some people write it as with this bracket. Not some people. Usually we write it like this. Okay. But this book, this notes uses these brackets. Don't worry, it's a notation. Now, what happens? What's the difference between this Kn and this S? When you look at the summation here, I equal to 1 to n mod xi. If I want to look at a corresponding thing in the sequence space, okay, if I have to look at this corresponding thing, then it will be summation I equal to 1 to infinity mod xi. But that creates a problem. Why? This is always finite because it's a finite sum. This one have a problem of convergence. Why? Because every sequence may not converge. For example, take the sequence 1, 1, 1, 1. Okay. This does not converge. This is not this series summation. So this is xi equal to 1 for all 1. Then mod of xi, I equal to 1 to infinity is infinity. So this series may not converge. So we have problems here. This problem we didn't had here because it's a finite sum. That's why you could define an Rm there. So what do we do now? We slightly use the previous theory and then do it here. So what we do is we take the sequence space. Okay. Now you look at 1 less than, you can take less than or equal to also. Okay. And then you define LP. Okay. This one is the set of all sequences in S such that the summation mod xi raised to p, okay, summation from I equal to 1 to infinity or 0 to infinity is finite. These are called LP spaces. How do you define L infinity? They are bounded sequences. Okay. So this is an additional condition that we have. Now, how do you define this convergence here? You say that X is in LP if and only if, okay, limit n going to infinity of summation mod xi raised to p I equal to 1 to n is finite. Exists? Exist means the limit exists and it is finite, right? This is the definition of it's series being convergent, right? So what do you have here? You have here this finite sum. This is called the nth partial sum. Okay, nth partial sum. This nth partial sum. This sequence, if you call it as Sn, okay, nth partial sum, this sequence converges. So essentially, what you do is you work on finite n and then take the limit. Okay, that's what I was telling you. So if you take x in LP and y in LP, what you do is you look at summation I equal to 1 to n mod xi yi. I hope you understand here. X is the sequence xi and y is the sequence yi. Okay. Now this n is fixed here. Okay. Now this will be less than or equal to by whatever the Hölder which we have done earlier. Is that it is less than or equal to this xi, this x, okay, I put some n here, all right, p into, so let me take a p prime. All right. Now you have here y, this n, p prime. So this particular thing, whatever this sum here, okay, what is this xn p I am talking of? What we mean here is this is summation I equal to 1 to n mod xi raised to p. And then I'll take a power p here so that I don't have. Now this you can write it as summation less than or equal to. I can add some more term here. So I get xi raised to p. This can be written because this x is in LP. This gives you this. Clear? So this summation, therefore, what we have here is this summation, okay, mod xi yi. Now at the moment it is finite sum I equal to 1 to n is less than or equal to the LP norm of, I'll prove that it's a norm. Okay, so I'm proving the Hölder norm here. So instead of you don't like the norm, I'll write here xi mod xi raised to p. Now I take infinity here, raised to 1 by p. Same thing. Now this is independent of n because I have already added up. So now you take the limit here. Okay, so take the limit as n tends to infinity. What you have is summation mod xi yi is bounded by summation xi raised to p mod raised to 1 by p into summation yi mod raised to p prime into 1 by p. That is what the thing is. This is called, so this now I can take I equal to 1 to n. So this is called the Hölder's inequality. For the LP spaces. Okay. Now condition here is that you take 1 over p plus 1 over p prime equal to. Usually you start working on 1 less than p less than infinity. P equal to 1, okay, but p equal to 1 and p equal to infinity, this is easy. Do it. If you don't get it, I will do it for you when I come to this one. Okay. That is what I wish to tell you here. If you do for the finite stuff, then the same proof carries over to the infinite stuff. So that's exactly what this person is doing here. Okay. Sequence spaces. So these are all sequences xi and yi. And when do you say a sequence is in LP? If summation I equal to 1 to n mod xi raised to p raised to 1 by p. If you don't have raised to 1 by p also, it's okay. If mod of xi raised to p is finite, then it is called in LP. How do you define the norm? He writes it as the P norm as one line. Normally, in many other books, they use two lines. This norm of mod of xi raised to p, you write it as summation I equal to 1 to infinity mod xi raised to p raised to 1 by p. If p is not infinity. If p is infinity, you take it as a supremum. That is the L infinity space. These p norms are not finite for all sequences. That's what I was telling you. So we define a subspace here. This is what I didn't want to rush through yesterday. So we define a subspace here LP or LP over K for which this LP norm is finite. You don't like the word norm, you say two lines and then X with P is finite. And you also define another space, sequence space, C0 over C0 K, such that set of all sequences for which the limit Xi is 0. Sequences which tend to 0. You should understand one thing here. A sequence xn goes to 0 if and only if sequence mod xn goes to 0. That is indirectly used. Because normally this is called convergent sequence space, convergent to 0. But you take only limit of I going to infinity mod xi. But it doesn't matter because xn goes to 0 if and only if mod xn goes to 0. Use that analysis. So what is the first order business? You have to prove the Hölder's inequality. That's what I did a minute before. Okay. Take the summation I equal to 1 to n instead of 1 to infinity. Use the Hölder's inequality and then you raise the summation from I equal to 1 to n to infinity on the right side and take the limit. Okay. So that's what he says. Apply the proposition 7.2 to partial sums and pass through the limits. Is it clear? Still I have not proved.
Yes, sir.
Okay. This is a simple matter. I will not do that. Okay. This is also a simple matter because this follows from what we have done. 7.3. Okay. What is important is the following. I will come to it and then I will again explain to you when I come to this. Okay. Little later. All right. So one important aspect is uh, let me it follows, let's put page 23. Okay. It follows that norm is a norm by passing through the limit in the finite dimension case. Same thing what I did for the Hölders. You use the Minkowski's inequality and then come through the same thing. Okay. All right. I hope you are getting me. Okay. Should I explain here this part? From finite dimension, how you get an norm? Okay, I'll do it. Otherwise, we should not get into the trouble. Okay. So you take a sequence. Okay, take a sequence. So you take a sequence x, xi, take a sequence y, yi, both in LP. 1 less than or equal to p less than p. All right. What does it mean? It means summation mod xi raised to p I equal to 1 to infinity. It's finite. Summation mod yi raised to p summation I, this is also finite. Now what you do is you take the partial sum. So you look at x1, x2, xn, and you look at y1, y2, yn. That is, I am taking the first 10 terms. Now I apply what we have done earlier. Okay, summation mod xi plus yi raised to p is less than or equal to, okay, summation mod xi raised to p, okay, plus there's a raised to 1 by p here. Okay, we take out this. This is raised to 1 by p plus summation mod yi raised to p raised to 1 by p. This we have done for finite sum. Okay, this is also equal to 1. Now, since infinite sum is finite, so this gives you apply that here. So this will be summation I equal to 1 to infinity, because I am adding some more positive terms. So instead of inequality still will work. The same story here. On this side, you have I equal to 1 to n. Okay. Now this is independent of n. Now take the limit here. So you take limit n going to infinity on the LHS. Okay. On the LHS. So what you get is summation mod of xi plus yi raised to p raised to 1 by p is less than or equal to the LP, the 2 lines of LP plus the 2 lines of whatever it is. Now this becomes now I equal to 1 to infinity. We are coming from finite sum to infinite sum, because this side is always less than or equal to helps you. So what is this stuff? This is nothing but norm of x plus y raised to p less than or equal to. Okay. Therefore, this these 2 lines p satisfies triangular inequality.
Sir, is the
Therefore,
power
this
at is below.
hello?
Sir, mod of x plus y, p is in power or p is in below, sir? p at
Huh?
norm or p is in power?
Huh? Sorry, thank you. It's just norm of it is p is here. Thank you. Yeah, there is no power p. Yeah, I understand what you are.
Yes, sir.
What he says is that this power p should not be there, which is correct. Is that okay now?
Yes, sir. Yes, sir.
Somebody told me to use the board, so I'm using the Rackham board here. So this shows that the LP spaces, this triangular inequality. All right. What is the other inequality you have? So if x is in LP, is sometimes we use below or whatever it is. Then alpha times x is also in LP. That's an obvious thing. Okay. Why? Because you take the summation, apply the definition always. Okay. Alpha times mod xi raised to p. This is the power, right? I equal to 1 to infinity. This will be actually equal to what? Mod alpha raised to p into summation I equal to 1 to infinity by the definition. Okay. Now you raise it to p. Raise it to 1 by p. So mod alpha, it is mod raised to p, raised to 1 by p. So when you raise it to 1 by p, you get a mod alpha here. And this will be the same thing raised to 1 by p. This is nothing but alpha x norm p is actually equal to mod alpha times mod alpha. So this property is also satisfied. So the last thing is that x is 0 if and only if the norm of xp is 0. It's obvious. Each term is 0. Therefore, the sequence itself is 0. Okay. Yes. Yeah, actually, we have shown only it's a norm. Have we shown it's a vector space? Yes, obviously. Why? Because sum of the two convergent sequences convergent, etc., etc. I will not do that. All right. Okay. So this is one interesting story that we have, but we can extend it to. So this is what we have done is for 1 less than or equal to p less than. What about L infinity? That's also a non-linear space. Also a non-linear space. Okay. Proof I will leave it as a homework. Proof is very simple. What is that you have to show? So what is the L infinity norm? So if you take x in L infinity, then you define norm of x infinity to be supremum of mod xi over I. This is the norm. So I leave it. There is a very simple affair to do. If you have two sequences, if both the sequences are bounded, the sum is also bounded. So if you have a sequence which is bounded and multiply by a scalar, that sequence is also bounded. So that it's a linear space is obvious. What is the zero element? Zero sequence is the zero element. So it becomes a vector space. No issues. Now if the supremum of mod xi is zero, obviously all mod xi will be zero. That means xi is zero. Therefore, the infinity norm of x is zero if and only if x is zero. That's also. The triangle inequality is a triviality. I will not do that. I will leave you as a homework. Reason why I don't want to do it is that if I do things which are simple, people don't like. They say that sir, we are all student, don't do trivial things to us. So I expect you all to be very good students, and therefore I won't do trivial things to you. Okay, that is the story with. And one important aspect which I will not do it here is the containment problem. So you have LP here. Okay. So you have here LP, okay, over K, and you also have LQ over K, and one is less than or equal to P, less than or equal to P. What is the connection? What do you mean connection? Connection means, is this true or is this true, and when? So these are the questions which we would like to ask. First question is very simple. If you take x in LP, okay, then the summation mod xi raised to p is finite. Right? I equal to 1 to infinity. Now this is an infinite series and that sum is finite. So this implies that mod xi goes to 0 as I goes to infinity. Yes or no?
Yes, sir.
if you have a series which is convergent, positive series which is convergent, nth term goes to 0. This will imply that this sequence X is bounded, right? It has to be a bounded sequence. If it's a bounded sequence, then this will belong to L infinity. So what is that we have shown? We have shown that LPK is contained in L infinity. What about the other way around? It's not true. Why? You take the sequence 1, 1, 1. This sequence is bounded, but it cannot be in any LP for all P. Right? That is the. So I will show you the other containment, LP contained in LP or LP contained in LP next time. Okay. Now, according to my time here, it is showing 12:55. So, but for a couple of questions, let us close the class for today because you may have something else at 1 o'clock. Sorry, again, there was a. Actually, the problem was there was some issue with the laptop. So they changed the browser from this. What is that browser? With usual browser that they changed it to Brave. Okay. Brave browser simply did not allow me to work with the Google Meet. That is why there was a delayed by 2-3 minutes. All right. That's okay. And we can make that later. Only suggestion to you is that there are many gaps which are left off in the class. Please complete those gaps. Don't leave it. Okay.
Okay, sir.
Any other comment you want to make it quickly before 1? Anybody? I can't send a message to you because I am not an administrator of your WhatsApp messenger. So that's an issue that you have to manage because I did not.
Sir, we can create another group for function analysis if it require.
There is no requirement. No, why are you unnecessarily creating human group? Otherwise, you add me as
Okay,
an administrator there.
okay, sir. Okay, sir. I will add you, sir.
Then there is no headache. Then I can send on message.
Okay, sir. Okay, sir.
Is it too fast or too slow?
Not
Can
too
I go
fast, not too.
faster?
No, sir. It is okay, sir.
So for another 10 lectures, I will go at the same place, but I will revise few things what I have done in the previous.
Okay,
Have a
sir.
good day. Bye.
Thank you, sir.
Enjoy yourself.
Bye.
Thank you, sir.